We'll begin a discussion afresh this lecture. Are there any questions about the remainder of last lecture? Questions? No. Okay, this lecture we are going to use substantially the same methods we used before to discuss the form factor. The form factor in this case means a generic three-point function. It need not be the nucleon or electron form factor. It could be the pion form factor. It need not be an electromagnetic form factor. It could be a strong interaction vertex function characterized by three momenta. P, P prime, and Q. I draw it as if it were electromagnetic. To avoid singularities, trivial pole singularities when P and P prime go on the mass shell, I will make this IPI. And we are interested in exploring the analytic properties of this. For P squared equals P prime squared equals some fixed real mass M squared, some stable particle mass. And of course, for practical purposes, the stable particle that is created by whatever field I have here, Q squared arbitrary. Thus, we wish to consider this as a function, the Feynman integral as a function of a single complex variable Q squared with P squared and P prime squared entering as parameters. Notice that there are, of course, only three independent inner products, and I can choose them to be P squared, P prime squared, and Q squared. The first question, at one stage in our argument, actually, we want to change this value M squared from the stable particle mass to a arbitrary value below the stable particle mass, but I'll keep denoting it by M squared. The first question we'd want to ask is, what is the physical region? Because although we've got a whole complex plane, which at the moment we don't know how to explore for singularities, we do know how to find singularities if they exist in the physical region. Well, in the physical region in particular, Q squared can be negative, or Q squared must be real. And I will argue that the physical region consists of all negative Q squared, or 0, and all Q squared greater than or equal to 4M squared. It does not, unlike the propagator, the physical region in Q squared does not include the entire real axis. The point is this. If Q squared is less than or equal to 0, and all the vectors involved in the problem are supposed to be real, that's the definition of the physical region, we can choose Q to be 0, Q. That is to say, we can, by a Lorentz transformation, make it a completely space-like spatial vector. Then we could choose P. Sorry, I forgot to write down the definition of Q. Q is, say, P minus P prime. We could choose P to be, for example, square root of M squared plus 1/4 Q vector squared, Q vector over 2, and P prime equal the same energy and minus Q vector over 2. Thus, our scattering process can be, these are obviously real vectors which obey all the conditions, and our vertex function can be thought of as a particle coming in, bouncing off of a brick wall, reflecting, changing its momentum, and transferring momentum Q to the brick wall. If Q squared is greater than 0, again, by a Lorentz transformation, we can choose Q to be, say, Q naught 0. And with no loss of generality, since the kinematics are time reversal invariant, we could choose Q naught to be positive. And then of course, we have a production process where momentum q comes in and makes two particles of mass m out of the vacuum. Energy is fed in. To be precise, I'll write down the actual momenta. P is 1/2 q naught square root of 1/4 q naught squared minus m squared times some, let's say, 0, 0, so they move in the x direction. P prime equals minus 1/2 q naught which obviously requires that q squared be greater than or equal to 4m squared. And that's what you would expect for a production process. Of course, if you are making a pair of particles, actually the minimum energy they have is 2m, and the minimum square of the energy in the center of mass frame is 4m squared. Thus we have, not saying nothing about analyticity so far, but just saying what regions of the complex q squared plane we can reach with real external momenta. Here's the whole big complex q squared plane. Here's the real axis. This is not supposed to be a cut. This is supposed to denote the physical region. We'll find out where the cuts are later. Here is 4m squared. This is the physical region. And this is the physical region. Notice it is impossible to reach this region, the gap, along the real axis with a real external 4 momentum, and that will cause us problems later on, problems which we will be able to solve, but which will lengthen this discussion beyond what it would be otherwise. Now, let's use our physical region Feynman rules to see what singularities we have in these two regions. Not Feynman rules, Landau rules. Remember last lecture I showed that in the physical region the Landau rules were equivalent to saying that the diagram, or any diagram obtained from it by short-circuiting, could be interpreted as a picture of a process going on in space and time with classical particles acting like classical particles should. So let's take the region q squared less than 0. There we have a particle coming in with momentum p. It is a stable particle, and therefore it cannot decay or do anything until something happens to it. The only thing that can happen to it is that it absorbs the external space-like momentum transfer q. So the first vertex in the diagram must look like this. On the other hand, classical kinematics is perfectly time reversal invariant, and by the same token, the last vertex in the diagram must also look like this. That is to say, the point where the momentum q enters the diagram after you've done all your short-circuiting must be the same point as the point where the momentum p is absorbed and the point where the momentum p prime is emitted. Therefore, the only kinematically possible graph is a completely short-circuited one, which, as I said last lecture, leads to no singularities. So we've got our first foothold in the complex plane. At least a negative real q squared axis is a region of analyticity. The case q squared greater than 4m squared is different. There we can consider both particles as incoming. By the way, I guess I'm making time run this way in these drawings, like in Feynman matrix elements, initial state on the right. We could have, if we consider, say, the two initial particles, time reverse of the situation I've written down here, two initial particles coming in and making the virtual photon or whatever with time-like momentum transfer, then there is a possibility that the two initial particles come together and annihilate. That's a possible process. Making a bunch of particles which do all sorts of things to each other and finally make the final momentum. Here, since the initial particles, however many they are, must be made at the same point, and they must all come together at the same point finally to hook onto the wiggly line, by the same arguments as given in last lecture, they must all be mutually at rest in the rest frame. Therefore, by the same arguments as before, the only singularities here are q squared equals sum of ma squared, where ma are some particles in the theory with the appropriate quantum numbers to come into this final vertex. That is to say, only normal thresholds. So of the two regions we can analyze with the equipment we have so far, one of them is chock-a-block with cuts, because in particular at the point 4m squared there is a normal threshold, and one of them is clean of singularities. Yes, sir?
Do you know where the thresholds are only from the phenomenology?
You have to know, well, if you're really doing order by order in perturbation theory, you know it because you know the masses of the various particles in the theory. Okay. You might worry, this is not a point I plan to raise at this stage, you might worry whether whether it really matters whether a particle is composite or fundamental, because of course you only see fundamental particles in all orders of perturbation theory. But one suspects, and this suspicion is verified whenever one can do rigorous arguments that don't depend on whether a particle is composite or fundamental, that you get the right locations of the singularities if you treat bound states as if they were fundamental particles. That's what you'd suspect. Somehow the bound states appear when you sum up all orders of perturbation theory. And you can imagine, say positronium, an electron and a positron exchanging an infinite number of photons makes a positronium pole. And whether you have that electron-positron, if you extract that singularity from the electron-positron ladder, that's the same as writing down a graph where the fundamental line where there is a fundamental particle with the quantum numbers and mass of positronium.
But isn't it we have to guess that we have the right theories and that the particles...
Well, we know, for instance, if we're studying the form factor of the pion, we happen to know, or the nucleon, we happen to know all the particles that are around, at least at the beginning of the cut. And as far as our dispersion goes, the fact that there are four branch lines along here is irrelevant. We just put the contour around them all. We have to know where the lightest particle is. And we do, empirically. And that's the only way we do. But I mean, that argument was in a sense getting a bit ahead of the game, because for the moment, to get a dispersion relation, we need analyticity in the whole complex plane. And all we know at the moment is that we have analyticity in some neighborhood of the negative real axis. So we've got to get into the complex plane somehow. And the device for enabling us to do it will be a Nambu representation. As you recall, the Nambu representation enabled us to write a Feynman integral as product over all internal lines to go from 0 to infinity, d alpha a. A numerator factor, which I'll quote n double prime, and had all sorts of complicated dependencies on the alphas, but was irrelevant because it was a numerator and free of singularities, times a denominator raised to the power I minus twice the number of loops. And that denominator was of the following form. It was all the independent inner products times functions of the alphas. Thus I have some function c of the alpha times q squared plus some function c prime times m squared, the only other independent inner product, minus sum on a, alpha a, ma squared from all the internal masses, and of course a plus I epsilon, but I'll drop that since I'm in a region of analyticity. Q squared greater than c. Now, I want to argue that in the region we have explored, q squared equals q squared less than 0.
Based 25, Duke.
To m squared, it is an undistorted contour in alpha. That is to say, we're integrating over real alpha. We know from our previous rule that we don't encounter any Landau singularities, that is to say any endpoint zeros or any pinch zeros in J, as we go from the Euclidean region up into this region, say by allowing p squared to go continuously from 0 up to m squared. But does that tell us that we don't encounter any zeros at all? That we don't have to move the contour on the way? I would like to argue that it does. The reason is very simple. We can get from the Euclidean region, where we know the contour is undistorted, to this region continuously, passing only through real values of q squared and p squared, albeit complex external momenta. In the Euclidean region, in particular, say at the point q squared equals 0, m squared equals 0, which is a definite Euclidean point, all external momentum vanish. You can't get more Euclidean than that. J is everywhere negative, aside from the trivial point where all the alphas vanish, where we know the numerator vanishes also. As we go up into the region we're interested in, suppose at some stage a 0 appears in the domain of integration. Well, if it appears in each variable, it must either come in from the end, that is to say from negative alpha, in which case it is an endpoint singularity in that thing, or it must appear someplace in the middle. Since the function is negative up until that moment, when a 0 appears in the middle, it is in particular a maximum of the function, and a maximum is in particular a place where the derivative vanishes. Therefore, if a 0 appears at all in the course of our transit from the Euclidean region to the region of interest, it must be either an endpoint 0 in each variable or a pinch 0 in each variable, but there aren't any because we've explored the Landau rules in that entire region. Therefore, the contour is undistorted, and in particular, J must be less than or equal to 0, or in fact less than 0. Now we're home, because it's obviously negative at q squared equals 0, m squared equals 0. I should say, except for the trivial point. Is equals 0. Now it's going to be trivial. I will argue that if imaginary part of q squared is not equal to 0, either positive or negative, this implies J is not equal to 0. Thus, with one fell swoop, we will be able to extend our domain of analyticity to the entire complex q squared plane except for a cut along the positive real axis. The argument goes as follows. Imaginary part of J is xi, a function of the alphas, about which we know next to nothing, but just enough to prove the statement. If this equals 0, that implies that there is some point inside the domain of integration for which C equals 0, some assignment of the alphas. Now let's look at that point. If at that point the real part of J equals 0, at that point somewhere in the domain of the alphas where C vanishes, then J equals 0 independent of q squared. Because if C, some real function of the alpha, vanishes at some point in the domain of integration, J is totally independent of q squared, since it depends on q squared only through C q squared. But that's impossible, because in particular we know for q squared real and negative, j does not vanish. Reductio ad absurdum. Is the argument clear? Good. Therefore, we have a very large domain of analyticity obtained for any diagram of arbitrary complexity just by following our noses using classical kinematics and the Nambu representation. And that domain of analyticity I will now sketch out. Q squared plane, the axes, a possible cut. It's analytic in the upper half plane, analytic in the lower half plane, analytic by our proof for q squared less than 0. About the positive real axis we know nothing, so it looks like this. We've got everything except the positive real axis. We know we can't eliminate the whole positive real axis. In particular, we know at 4m squared there is going to be a branch point. The question is, what about the gap? The region between 0 and 4m squared. That's where we're going to have to work, because none of our rules and none of the tricks we've gotten so far enable us to penetrate that gap and see whether or not there are singularities there. Let's make some preliminary guesses about what we expect. Guesses. Suppose the external particle is the pion. We're studying the electromagnetic form factor of the pion. The pion is the lightest particle, so we would expect analyticity in the gap somehow. What else, after all? What could happen from our experience with the propagator? We would expect only normal thresholds. So for the pion, we'd expect analyticity for q squared less than or equal to 4m pi squared. Perhaps I should say less than. And therefore, we would expect, in the case of the pion, these are naive expectations, that the gap is in fact a region of analyticity. We just have to be clever enough to prove it. For the nucleon, well, for the nucleon, we wouldn't expect the gap to be a region of analyticity. The gap, after all, goes up to 4 mass of the nucleon squared. But we know a nucleon-antinucleon pair can go into a pion-antipion pair, or a pi plus pi minus pair, and therefore we'd expect, again from our experiences with the propagator, for there the region of analyticity that will again be q squared less than 4m pi squared. And the gap will have real singularities in it. Now, what about, treating for the moment just for educational purposes, a composite particle as fundamental, the deuteron? There we will find a surprise. Our intuition would be that the lightest singularity on the base of the propagator would be associated with the 2 pion intermediate states and would be at q squared less equals 4m pi squared. But in fact, there will be a lower singularity, as our analysis will demonstrate in the case of the deuteron, the famous anomalous threshold. Anomalous because it's got nothing to do with making pairs. But that's a warning. I'm going to derive it in the course of the next half hour or so, but I tell you about it now. Now, we have to penetrate the gap, and the gap is not a region that can be attained with real external momenta, nor can it be obtained with Euclidean external momenta, since obviously some of the vectors squared are positive, not negative. However, it is a region that can be obtained with what I will call, and I should warn you this is my own ad hoc terminology, but it's useful to have something there. The so-called pseudo-Euclidean region. This is defined as a region in which the imaginary part of all external momenta are equal to 0 in their time parts, and the real part of the space part vanishes. It's just the opposite of the Euclidean region. We can, of course, get to the pseudo-Euclidean region from the Euclidean region simply by making a rotation, just as we got from the Euclidean region to the physical region. Where alpha goes from 0 to pi over 2. Except instead of just rotating the phase of the time component, we rotate the phase of all 4 components. Thus the time component, which is imaginary in the Euclidean region, becomes real, and the space component, which is real in the Euclidean region, becomes imaginary. By the same arguments as we use for rotating from the Euclidean region to the physical region, there are no zeros can possibly appear in the denominator up till the very last stage of this process. So just as in the physical region, in the pseudo-Euclidean region, we have an undistorted contour in the Feynman representation of the integral. The alphas are real. Yes, the alphas are real, and the internal momenta obey the pseudo-Euclidean condition written down here. Thus, just as we had a set of Landau rules specialized for the physical region, we could get a set of Landau rules specialized for the pseudo-Euclidean region. The most convenient way to phrase these is to introduce a variable Ka twiddle, which will be a real vector, such that Ka twiddle naught equals Ka naught, and Ka twiddle space part equals Ka space part. No, these are the internal momenta.
Oh.
Okay. And then our rules are Landau rules for pseudo-Euclidean region. There will be 4 of them, just as before, assuming all our diagrams have been short-circuited, so I don't have to write the case alpha equals 0. Around any closed loop, sum of alpha A, K twiddle A equals 0. It's true for the Kas, and the Ka twiddles just differ by factors of I in various components. Ka twiddle squared, where now I mean square in the Euclidean sense, the sum of the 4 components, the I supplying the minus sign that's normally there in the Minkowskian metric, equals Ma squared, 3, Ka twiddle equals Ka twiddle star for alpha A greater than 0, since we're taking care of 0 alphas by doing the short-circuiting trick. Okay, any questions about this? I haven't yet shown that the region in the gap is described by pseudo-Euclidean momenta. I'll do that after I finish my analysis of pseudo-Euclidean momenta. Actually, as I passed my notes, I see I was originally intending to do it before, but forgive me this pedagogical lapse. We'll get to that point in a moment. Now, In the pseudo-Euclidean region, these are very similar to the four equations that we encountered in the physical region last lecture. The only difference, in fact, is that this is the Euclidean norm rather than the Minkowskian norm. Otherwise, the rules are identical. And this means we can go part way towards getting a representation of these rules that we can get some feeling about. In particular, we could define delta A, the separation, as alpha A, Ka twiddle A. And thus we would construct, since that separation by loop equation obeys, well, firstly, it's a real number, and it obeys all the, you go around the closed loop, it adds up to 0, as it should. We could construct from every Feynman, we could interpret every Feynman diagram in this rule as being a geometric figure, not a process in Minkowski, not a geometric figure in Minkowski space, which is a process, but a geometric figure in Euclidean space, with points associated with every vertex and with lines given by this formula, and the whole thing comes up and makes some sort of rigid body, some complicated structure like a Fuller dome or something like that. I wish I could give a simple interpretation of the alphas corresponding to the one I gave last lecture for the physical region. I struggled for a while trying to interpret them as direction cosines or something like that, but I couldn't see any, so we won't be able to give a complete geometrical interpretation of all of the Landau rules, but we will at least have this partial geometrization that this rule and this rule say, and the reality of the alphas, say that from any Feynman graph or short-circuited Feynman graph, we can construct a geometrical figure, and thus our arguments about the locations of singularities, which in the physical region involve kinematical arguments involving classical kinematics and times and so on, here will turn out to play an important role. Such theorems as the sum of the angles of a triangle is 180 degrees. And all of Euclidean geometry will come to our aid as classical kinematics came to our aid last lecture. Now, the part I forgot to do, and made myself a bad pedagogue, was demonstrating that the gap can be attained with a pseudo-Euclidean external momenta. The easiest way to do it is just to write it down. P is supposed to have a real time part, and that's real. Theta is an arbitrary angle, which I'm going to adjust. An imaginary space part, which I'll choose to be Im sine theta. That's certainly my freedom. P squared is m squared. The minus sign in the metric cancels the minus sign from the I squared. P prime, I'll choose to be m cosine theta minus Im sine theta. 0, 0. That's certainly pseudo-Euclidean, and of course Q is therefore pseudo-Euclidean. Equals, the I cancels the metric, the I and the vector component cancels the minus sign in the metric. I've got two of them, so that's 4m squared sine squared theta. Thus, I see as theta goes from 0 to pi over 2, for example, q squared 4m squared, precisely the gap. So the gap is obtainable with pseudo-Euclidean things. I'm sorry, the order got wrong. I was supposed to say this part first and then go into the dynamics of finding singularities in the pseudo-Euclidean region, but they should be both in your heads now, and I trust you are able to rearrange them mentally. Okay. Are there any questions about this? Okay. Now it's time for a little Euclidean geometry. We wish to study the singularities in the pseudo-Euclidean region, and that means we have to study a geometrical figure made up of our Feynman graph. There will be one vertex where Q comes in, or I should say Q twiddle, since that's a real vector, one external vertex where P twiddle comes in, and one external vertex where P prime twiddle comes in. These are 3 points in Euclidean 4 space, and therefore they define a triangle. I'm not saying that's the graph. The graph may be much more complicated, but 3 points certainly define a triangle. I will now argue that the graph has to lie completely within this triangle. Okay. That is to say, it's got to lie in the plane defined in which the triangle lies, and it's got to lie, it can't bulge out of the triangle. Let's consider a typical situation where we try and draw a graph that lies outside the triangle. I drew it badly. It's supposed to be a tetrahedron, some short-circuited graph. It's got a point that comes up. Now remember, all the alphas are positive. Okay? That means at this point, where all these point up here, the highest point, where all 3 vectors point downwards, the 3 associated k's also all point downward along the lines, because the alphas are positive. On the other hand, conservation of momentum says the sum of the k's at this vertex must vanish. That's impossible if they're all pointing downward. Is that clear? You cannot sum up 3 downward pointing vectors to get 0. You can't sum up 42 or 7 of them either. There's no way you can have a point that lies outside the plane. So this is an impossible situation. By exactly the same token, a situation where we have, so now we can stick to a plane, a situation where we have some sort of vertex that bulges out of the triangle, say coming out like this, God knows what, is also impossible, because again, we look at the farthest vertex that lies outside the triangle. All the momenta are aligned along the separation vectors because all the alphas are positive, and they cannot possibly sum up to 0. Therefore, we have a triangle. And all the vertices, no matter how complicated the graphs are, as a consequence for the pseudo-Euclidean region Feynman rules, must lie inside that triangle. It's not going to look like a fuller dome after all. Okay. Is the arguments clear to everyone? I gave them in words rather than writing them on the board, but are they clear? Now the second stage. This triangle could be either degenerate or non-degenerate. That is to say, the 3 vertices, 3 points could lie in a line, which is a degenerate triangle, or the 3 points could be, no, I'm not going to define it as degenerate that way. 2 of the 3 points could coincide, or the 3 points could be different. Let's assume for a moment the 3 points where the 3 external momenta come in are different. Now, we have a triangle, and it is a characteristic of a triangle in Euclidean geometry that it has 2 acute angles, at least. It cannot have 2 obtuse angles nor 2 right angles, because then the angles would add up to more than 180 degrees. There are also 2 vertices where the stable particle comes in. Okay? Therefore, there must be one vertex acute corner with P twiddle or P prime twiddle entering.
Yeah, drop it out in the dirt.
It's got to be that way. That's Euclidean geometry and also counting possibilities. They can't both be obtuse or right. Now, I'll erase these rules, but I presume you remember them. Now, maybe you don't, so I better let me work here. Let's focus with our magnifying glass on that vertex. Here is an acute angle. Here is, let's say, P twiddle coming in. The whole graph must lie within this acute angle, so therefore we have a spray of particles coming out. I don't know how many, 42 maybe if it's a complicated graph, but they all must lie within that acute angle. K1 to Kn. K twiddle 1 to K twiddle n. P twiddle, by energy momentum conservation, is sum of K twiddle A equals 1 to n. Therefore, P twiddle squared equals sum of the squares, MA squared, plus sum A not equal to B, K twiddle A dot K twiddle B. Now remember, the alphas are positive, so the k's are always aligned along the separation vectors. The arrows are as I have drawn them. And since this lies within an acute angle, these inner products are always positive. And P twiddle squared is, of course, held fixed at m squared. Thus I have m squared greater than or equal to sum of ma squared. Any questions? It's just Euclidean geometry. It's a statement that it's an acute angle. Yes?
I'm still a little confused about this part. These are four-dimensional vectors we're adding up, right?
Yeah, but they all lie in a plane. That was the first thing we proved, that this configure...
That's what I'm worried about.
Hmm?
That's what I don't quite see. I can see that in three dimensions.
The same thing in 4. It doesn't matter. It defines a plane, call it the 1-2 plane, label things 1, 2, 3, 4. Consider the point, the vertex in the graph, which has the greatest value of x3. I'll show that that's 0. Okay.
Oh, so we choose the...
Yeah, choose a direction.
Oh,
Okay. All the vectors coming out from it must point towards the... Okay. And the sum of their x3 components must be 0, and therefore x3 is, etc. Now, is this possible for the particle? Suppose we are working with the theory of pions and nucleons and deuterons and lambdas and k's and sigmas and whatever. Is this possible? It's certainly not possible for the nucleon, because the nucleon is the lightest particle carrying nucleon number 1. Therefore, everything it can decay into, anything it can go into must be a nucleon plus a bunch of other stuff, and that's an impossible condition. It's also not possible for the pion, because the pion is the lightest strongly interacting particle of all, if we neglect weak electromagnetic interactions, as I guess I'm doing, and there's nothing it can do that can do that. However, it is possible for the deuteron, because in particular the deuteron mass is approximately is a little bit less than twice the nucleon mass, and a deuteron can go into a nucleon, a neutron, and a proton, for example. And 4 nucleon mass squareds minus a little bit is certainly greater than 1 plus 1 nucleon mass squareds. Is everyone with me? It depends upon whether, given the particles in the theory, given the particle whose form factor you're studying, whether it is possible or not possible to attain this condition. It is not possible for the pion, it is not possible for the nucleon, it is possible for the deuteron. Is everyone happy with that? It's just arithmetic, but people are looking blank. Are you looking blank because it's so simple you're bored, or looking blank because you don't follow the argument? This part of the argument is in Dworkin and drill. We need not worry about the graphs where the 3 points are distinct, the reduced graphs, and we have to worry about reduced graphs where 2 points coincide. That means the triangle is degenerate and becomes a line. If the 2 points are Q and P, or Q and P prime, we're cooked the same way as before, because then the other one, P or P prime, is at an acute angle, indeed the most acute possible of all angles, 0. So we need only worry about the case where P twiddle and P prime twiddle come together at the same point. Everything lies within a line. I can't draw it without making it bulge, but it really doesn't bulge. They're all on top of each other. It's not a geometrical figure at all. It's like cable or something. A bunch of lines stuck together, and then Q twiddle comes out here. Now, Q to all momenta are aligned with all separations, and therefore all 4 momenta are aligned, and therefore Q twiddle squared equals Q Euclidean, I should write, equals Q squared equals sum of MA squared, where MAs are the masses of all the particles coming in here, because they're all line vectors and they're all of length MA. That is to say, this is just a normal threshold again. Thus, we have proved to all orders of perturbation theory, all orders, these methods are really ingenious. They were clever fellows who thought them up circa 1960. These methods are really ingenious. To all orders of perturbation theory, 147th order of perturbation theory, the most complicated graph you could think of in the theory of pions and nucleons. The darn thing is an analytic function of Q squared, the form factor, aside from a cut beginning at 4 times the mass of the pion squared. For the pion form factor, and of course for the nucleon form factor, also the same thing, 4 times the mass of the pion squared, except that's outside the physical region. But nevertheless, it's a normal threshold caused by a graph that looks the same, although the interpretation, as we have seen, is a little bit different. Any questions about this? It's groovy stuff, okay? It's just, you're back in high school, you're doing geometrical theorems, and it gives you analyticity information. Yes?
When you say that n squared is greater than or equal to the sum of the NA squares, can you tell anything else about where the singularity is?
Yes, we'll investigate it now. That's the next topic. Okay. Okay. We now turn to the case of the Deuteron. And I will investigate a typical graph that contains, planar graph, to see if it contains a singularity. It may contain a singularity that's greater than, of course, 4 times the mass of the pion squared, and then that's irrelevant. That doesn't, it's the lowest one that tells us where we've got to begin our dispersion interval. Yes, sir?
Is the squares supposed to be inside the triangle?
No, outside. They're all aligned. That's right. So the length of the sum is the sum of the lengths. They're aligned. It's like going, 40 feet this way and then another 30 feet this way. Okay. The length of the sum is the sum of the lengths, not the sum of the square. It's not that the square. They don't make right angles. No. Now, okay, so now we will begin. We will find, in fact, that for the specific case of the Deuteron, there is a singularity that lies lower than 4m pi squared, and this singularity, which will occupy us for the rest of this lecture, not because it's really that important in practice, but it's a groovy application of these methods, is called the anomalous threshold. What I will do in the remainder of this lecture is first compute the location of this thing for the simplest graph in which it occurs, involving a Deuteron, and then explain its physical as a pure mathematical computation, and then explain its physical meaning in two different ways. So you will end up wondering why it has such a funny name, anomalous, when it's such a natural object. This is the historical order. First it was discovered, and then it was explained. Okay, let's take a simple case. I may give you a homework problem, which I'll show you, which you show that for the Deuteron, this is the lowest of the anomalous thresholds, but I'll just analyze a particular graph. Deuteron comes in, decay, say, into a neutron and a proton, treating it for the moment as if it were a fundamental particle, just the kinematics that are of interest. Photon goes in and hits the proton. Okay, I'll call the mass of the Deuteron, which I've been calling little m up until now, capital M. It's the external mass. I'll take the mass of the neutron and the mass of the proton to be equal, and I'll call them m, just to simplify the computation. It can also be done with all the masses unequal. Now, let's focus attention at one of these vertices, say the bottom one. Here's the Deuteron coming in. Here's a neutron and a proton. The momentum of the Deuteron, let's have an angle here, which I'll call theta. Momentum of the Deuteron squared by momentum conservation is the momentum of the neutron squared plus the momentum of the proton squared plus 2 pp dot pn. And those should all, of course, be twiddled, since we're in the pseudo-Euclidean region. This is m squared plus m squared plus 2m squared cosine theta. Thus we deduce the angle theta. The angle theta is given by m squared over 2m squared equals 1 plus cosine theta. That's the first part of our geometrical exercise. The angle theta is fixed. Okay? Notice, by the way, that it's important that the sum of the squares condition is fulfilled. If this number were less than 1, we would be in serious trouble with this angle. Now, since theta is uniquely determined, if we go back to our big triangle, this is so lovely. It's just geometry, P, P, N, gamma coming in. If this angle is theta, all the arguments also apply at this one, which is also theta, and therefore this one is pi minus 2 theta. Therefore, q squared, by applying the same reasoning to the third angle, q squared is m squared plus m squared plus 2m squared cosine pi minus 2 theta. They're both going in, okay, so it's the same thing. Thus, this is 2m squared, 1 plus cosine pi minus 2 theta, which is 1 minus cosine 2 theta, equals 2m squared. What is cosine 2 theta? I wrote it down as 2 cosine squared theta minus 1, 2 minus 2 cosine squared theta. Let's remove those pejorative remarks. Equals 4m squared, 1 plus cosine theta, 1 minus cosine theta, equals, well, now I've got it all, 4m squared, 1 plus cosine theta is m squared over 2m squared, and 1 minus cosine theta is 2 minus 1 plus cosine theta, 2 minus m squared over 2m squared. And this combines together to make this m squared cancels this one. This 2 cancels the 2 there. So I've got capital M squared as a common factor, 4 minus capital M squared over little m squared. Okay? Is this point clear? This is the location of the anomalous threshold obtained by high school level Euclidean geometry. I should say a little trigonometry also. But now the first thing we observe is that this could be well below the normal threshold, lowest normal threshold, if the Deuteron is sufficiently weakly bound. Because, in fact, as the Deuteron becomes unstable, as m squared goes to 4m squared, as we imagine adjusting the strength of the binding force between the proton and neutron that makes the Deuteron, q squared goes to 0, which is clearly well below 4m pi squared, and the Deuteron is indeed very nearly unstable. It's only very weakly bound, so q squared is quite low. Indeed, we can get an approximate expression for the thing, for a very weakly bound particle like the Deuteron. Deuteron, or generically a weakly bound particle, by saying m is 2m minus epsilon, where epsilon is the binding energy, and assuming epsilon is much less than m, expanding out and retaining terms only linear in epsilon, we find m squared, well here 4 little m squared, that's got a 0th order term, 4 minus 4 m epsilon over m squared, sorry, plus, because it was a minus sign up there, and dropping the term of order epsilon squared, or 16m epsilon. And is that right? Yes, that is right. Thus, in the actual case of the Deuteron, which is bound by what? Does someone remember, around 5 or 10 MeV? What? 8 MeV? 2.18 MeV. Well, that's much less than m pi. Even 16 times the nucleon mass times that is much less than the square of the pion mass, since 2.18 MeV is around 75th of the pion mass. Now, now, so much for the computation. It was clear and unambiguous and was very slick, but as characteristic of slick things, it does not give us much insight into what is going on. So therefore, I would like to give two arguments that will enable you to understand the physical meaning of what this anomalous threshold is. Let's see, I'll need this, so I'll reproduce it up here, and then I can erase the board. M squared. Two explanations. One would be, suppose the Deuteron were unstable. Of course, in that situation, we would be foolish in computing the form factor of the Deuteron. If it really were unstable under the strong interactions, there would be hardly any, no one could measure its form factor, and it would be a silly object to talk about. But suppose, but we could write down the graphs. I mean, there's no harm in that. Suppose m greater than 2m. In that case, this singularity moves into negative q squared, that is to say, into the physical region. And therefore, we could use our physical region rules for finding the singularity. Maybe we don't understand the anomalous threshold, but maybe we can understand this descendant, what it becomes as the Deuteron becomes unstable. Well, suppose the Deuteron were unstable, and let's consider exactly the same graph I have written down there. This graph is now interpretable as a graph of a process going on in space and time, because it's in the physical region. That's the physical region Landau rules. In fact, I'll just write it down and reread it. This is now Minkowski space, not Euclidean space, and this is time. A Deuteron comes along and decays into a neutron and a proton. I go into a Lorentz frame in which the decay neutron is at rest, as drawn. The proton travels around until it meets the photon, which has a contract as a hitman, and hits the proton, reversing its momentum, spatial momentum. So it goes back again, bouncing off a brick wall, represented by the photon. It goes back again until it meets the neutron, which has been placidly waiting there, and they recombine together to make the outgoing Deuteron. That's a 100% guaranteed physical process. Now, what is the kinematics of that process? The neutron is at rest, so its momentum is m0. The proton must have, if I say Q, I'm doing it in a brick wall frame, so Q is purely space-like, say 0 minus Q. The proton must have momentum Q over 2, so when it accepts momentum Q, its some momentum will be reversed. And therefore it must have square root of m squared plus 1/4 q squared as its energy. Now the two form momentum must sum up to make a form momentum of the Deuteron. How did I compute that? Ah, here we've got it. Okay. Pn plus pp squared equals 2m squared plus 2 to pn dot pp. I have a feeling this isn't the most efficient way, but I was getting tired. Must equal m squared, the mass of the Deuteron. Thus, pn 2pn dot pp, which we see from here, is m root m squared plus 1/4 q squared must equal capital M squared minus 2 little m squared, and a 2 here. Squaring both sides, I obtain 4m squared m squared plus 1/4 q squared equals capital M to the fourth minus 4m squared capital M squared minus 4 plus 4 little m to the fourth. I observe the m to the fourth terms vanish on both sides. This is q vector squared. And thus I find q squared, which is of course minus q vector squared, equals, the 4's cancel. There's a little m squared which I'll divide out in a minus sign. So I get capital M squared as a common factor, 4 minus m squared over little m squared. This is, of course, the same formula we have sitting right next to it, obtained by completely different reasoning. Of course, one set of reason, one is the rigorously applicable reasoning when q squared is positive, i.e. when the Deuteron is stable. The other is the rigorously applicable reasoning when q squared is negative, when the Deuteron is, q squared, one is rigorously applicable when q squared is negative, i.e. when the Deuteron is unstable. Nevertheless, they go smoothly and continuously, indeed analytically, into each other. The anomalous threshold, which has an interpretation in terms of triangles, in the case when the Deuteron is stable, goes into a singularity which has a perfectly physical interpretation in terms of physical processes that could actually go on when the Deuteron is unstable. Any questions? What could be simpler?
What does the singularity look like?
It's a cut. It's a branch point.
What's the physically?
When you actually do the experiment? I mean, how would I determine the singularity? Well, I mean, in momentum space, as I say, it's a if the Deuteron were unstable. Well, in momentum space, it is, as I say, a cut. The sign of it is, if you wanted to physically determine it, and if you had a Deuteron beams, you would take this photon, in position space, you take this photon thing, your source of photons, and move it around, and then you get an enormous response in your Deuteron detector up here, if the photon were lined up just right, i.e. had just the right momentum for Deuteron decay. And it would fall off more rapidly than a pole singularity. A pole would give you something that would fall off like inverse power var, typically. And this will give you something that will fall off as a higher power var, as the product of two exponentials with a higher power var in the denominator, because it's a two-particle singularity. Is that the sort of answer you wanted, or?
So if you did an electron Deuteron experiment, you'd see a peak?
Yeah, you'd see a peak. If the Deuteron were unstable.
Oh, now how about if the Deuteron is stable?
Well, this is in an unphysical region.
Oh.
Okay, it has to be included in your dispersion relation. It's like a T-channel pole, which is also in an unphysical, or an S-channel pole, which is also in an unphysical region. Okay, you might make a bump in the electron scattering amplitude if it's not too far below the normal threshold. We'll get much more insight into that in the next explanation, because I said I was going to give you two explanations, and I've given you one. Was there something else I wanted to say? Oh yes, we can also see what happens at the other end when m squared equals twice little m squared and the anomalous singularity disappears. Remember, we have this condition, m squared must be greater than twice little m squared for the anomalous singularity to be there at all. As m squared goes to 2 little m squared, q squared goes to 2 little m squared. Right? Because this is 2 little m squared, goes to 4 little m squared, excuse me. That is precisely the location of the normal threshold associated with the nucleon, with the 2 nucleon singularity. And therefore, we see what happens to the anomalous threshold when it dies, as we imagine the Deuteron becoming more and more strongly bound until the anomalous threshold condition disappears. If you followed it along, it would propagate along the real axis, and then there would be a branch point associated with the normal threshold, and it would duck underneath that branch point and escape from our view. can't just disappear like that. It's got to have some place to make its exit. And it makes its exit by cutting through the cut. Just like a stable particle, when you change the parameters of the theory so it becomes unstable, a stable particle pole makes its exit by going through a continuum cut. Hides behind the cut, behind the curtain, and disappears. Okay, we wanted to make that remark. Now, next remark. This singularity should be understandable in completely non-relativistic terms. This singularity is something we should see in non-relativistic quantum mechanics. Because after all, if the Deuteron is weakly bound, a non-relativistic situation, then the anomalous singularity is at a very, very low value of q squared, which is something that should be governable by non-relativistic reasoning. If it were at some gigantic value of q squared, we'd say, who trusts non-relativistic physics? But it isn't. It's at a very, very small value of q squared when epsilon is very small. And if non-relativistic physics is good for describing anything, it should describe physics as small values of q squared. Therefore, let's look at a non-relativistic description of the form factor of the Deuteron. I'll make everything spinless in an S-wave to avoid inessential complications. And I imagine I have a proton and a neutron. X is the proton position variable. This is real good, honest, non-relativistic physics with P's and Q's. X is the proton position. Y is the neutron position. P is a Deuteron state. Momentum P. The analog of the current operator at 0, whatever operator we're looking at, electromagnetic current and so on, is simply delta of x because the proton is charged and the neutron is not. That is the operator which, when evaluated between two proton states, gives you the charge density at position x. I should say J naught. That's the obvious object to look at. And that's the thing that comes into electron scattering off of an atom, etc. Now, we wish to compute, for example, minus p, delta of x, the operator, p. That will be the analog of our form factor for q squared equals minus 4 p squared, where p is the magnitude of p, because that's the momentum transferred. The momentum transferred is 2p, and it's space-like. Is this clear to everyone? This is how we set it up. That's the right non-relativistic analogy to make. Well, this is easily done if we have the Schrödinger wave function of the Deuteron. Indeed, we do. We know that in don't want to erase that. Go over here. That's what I want to compare with.
You already got it over there where you were about...
No, I want the non-relativistic limit. 16 m epsilon. I'm going to get that 16, every goddamn power of 2. Okay. Now, the non-relativistic state is, of course, the non-relativistic wave function, xyp, is, firstly, a center of mass factor, e to the minus ip, I guess it's plus, dot x plus y, I'll call this, for shorthand, psi sub p of x comma y. EIP dot x plus y over 2, that's the total momentum times the center of mass location. And then there is the relative wave function, which I'll call psi. That tells you it's in a Deuteron state. And that, I'm assuming the Deuteron is an S wave, just for simplicity. So that depends only on the absolute magnitude of the difference, x minus y. I know something important about the behavior of psi. from the fact that the Deuteron is a bound state, psi of r, as r goes to infinity, goes to some constant that I'm not particularly concerned about, some normalization constant, e to the minus on some number, kappa r over r. That's the well-known behavior of S-wave bound states at infinity. And kappa is determined exclusively in terms of the binding energy epsilon. Kappa squared over m equals epsilon, the binding energy. Why do I have m here and not 2m? Because it's twice the reduced mass, the mass in the center of mass frame, and if I have two equal mass particles, the reduced mass is half the mass of either one. Okay, now we're ready to go. We can compute the form factor. No matrix element is easier to compute than that of a delta function. We just say that is integral d cubed y, there's no y dependence in the operator, psi sub minus p star of 0 and y, psi sub p of 0 and y. That's the delta function. And plugging that in, hoping I get the right answer. I see I'm getting a minus p and p. The x dependence is irrelevant. I've got a y over 2 from one and a y over 2 from the other. So I get integral d cubed y. The 1/2s cancel, e to the I p dot y. And then I have psi of the magnitude of y squared. Everyone happy? If I call the magnitude of y r, I can of course trivially do the angular integrations, and I obtain proportional to r dr from 0 to infinity by standard trick sine pr psi of r quantity squared. Now this defines the object in the region in which it is physically defined for real values of p. However, we could continue this to complex values of p. After all, why not? In fact, we could continue it to imaginary values of p. However, we'll run into trouble when p gets to be too large and imaginary, because then the blow-up of the sign, which occurs for imaginary values of p, will not be canceled by the fall-off of the wave function at large r. Since the wave function is falling off exponentially at large r, if p gets too big and imaginary, the sign will blow up faster than the wave function falls off. Therefore, there is a singularity, if we go to try and analytically continue this along the imaginary p-axis, at p equals I kappa. Because that's when, p equals 2I kappa, because this is squared. So, therefore, I have a singularity at q squared equals minus 4p squared equals da 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 da. I cancels the minus sign. 4 times 4 is 16 kappa squared equals 16m epsilon. Da-da.
You said you get all the powers of 2, you're missing 8.
No, 16m epsilon.
Yeah, but you said you get all the powers of 2. I thought
No, I get the full 16. I'd get all the 4s and 2s and everything right, because I did it 3 times before I did. Thus, we see exactly the same location, it's of course exactly the same phenomenon. It has to be the same location, because if the Deuteron is weakly bound, non-relativistic physics should be applicable, but relativistic physics is also true. So any result we get by taking the non-relativistic limit of relativistic reasoning should correspond to the result we get from non-relativistic reasoning, and it does. Now, from the viewpoint of non-relativistic physics, there's nothing anomalous about the anomalous threshold. If nobody had ever invented relativistic quantum mechanics, or if at some very early date, say 1928, people were studying the analytic properties of the electromagnetic form factors of atoms, which they could have after all, historically, they just didn't, then this is the singularity they would have found. This would be the normal singularity. From the viewpoint of non-relativistic physics, the anomalous singularity is what we've been calling the normal threshold, because that's associated with particle-antiparticle production, which could hardly is a very anomalous phenomenon from the viewpoint of non-relativistic physics. So really, you see, you've just been brainwashed by this course. This thing that looks so peculiar and difficult to understand is actually the simple non-relativistic object, and this thing that looks so simple and easy to understand is in fact the complicated relativistic object. And I have reached the end of my lecture. Next lecture we will apply exactly the same techniques with no modifications to study the analytic properties of scattering amplitudes and perhaps say some things about pion-nucleon scattering.
When is the next probe coming up?
Next